Hello.
Hello, Sri. Am I audible?
Hello. 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 Am I audible? Hello.
Hello.
Hello. Hello. Am I audible? Hello, Prince. My screen is visible to you? Hello. Hello.
Yes, sir.
Okay. It is clearly visible?
Yes, sir.
Okay.
Yes, sir.
Okay. So within 2-3 minutes, we are going to brush up the previous lecture content. In the previous lecture, we have started with unit 2, that is transfer function determination of armature control DC servo motor. Okay. So what do we mean by armature control? Armature control means during the armature control, we are keeping the field quantity constant and varying the value of armature quantity. Okay, so with this concept, we have started with the derivation, that is transfer function determination of armature control DC servo motor. So first we have drawn a armature circuit, its equivalent circuit. So it has its own resistance RA, inductance CLA, then armature. Okay, so this is your armature circuit, and input voltage is applied to armature is EA. Okay, Then this is the shaft of your armature. So your armature having own moment of inertia and frictional force F0. Then as armature control, so therefore we are keeping the field quantity to be constant. So therefore your field winding is supplied with a constant voltage source, that is VDC. Therefore, current run by field winding IF is remain constant. Okay. Then let's say the current flowing to field winding is IF. Okay, so this is the loop we are getting. So this is a simple circuit diagram of armature control DC servo motor. So why this is called as armature control? Because we have applied input to the armature and we have kept the armature quantity, field quantity to be constant. So this will give you theta. This is the motor torque EM. Okay. So what are the steps to derive the transfer function of armature controlled DC servo motor? We know that the transfer function can be defined as it is the ratio of Laplace of output to the Laplace of input. Okay. So what is the input provided in case of armature controlled DC motor? Anybody?
EA of S.
Right. So input is applied to the armature winding. So therefore its Laplace transform is EA of S, and the output of the machine is, that is the displacement of the shaft, that is theta. So therefore the transfer function can be defined as ratio of Laplace of output to the Laplace of input. So therefore we are interested in to find the ratio of theta of S upon EA of S. Okay, so now in order to derive the relation between theta and E of S, we may use our simple fundamental rules. Okay, so first we start with the concept of torque equation. Okay, so we know that torque in case of DC motor is directly proportional to I into IA. Okay, where in case of armature control motor, the total field flux developed by the motor is directly proportional to field current IF. And as field current IF is constant, so therefore flux developed by motor is also constant. So this proportionality constant we have defined it by KF times IF, or sometimes K1, okay, KF time IF. Okay, so substitute this value here. Again, this proportionality we have defined by another constant. So take another constant K1. So it could be K1 KF IF into IA. So this will be given equation number 1 or 1, 2 or 3. Okay, so this is your torque Tm. Okay, so this is the first step. Then in the second step, we have determined the expression for back EMF EB. So back EMF EB is directly proportional to the speed. So therefore we say that EB is directly proportional to omega. Okay, and omega is nothing but rate of change of angular displacement with respect to time. Here theta is the angular displacement. So therefore we may also define it by, it is d theta by dt. Okay, so therefore take down the Laplace transform. So this will be our another expression. Then next one is we have apply Kirchhoff's voltage law KVL to this loop L1. So apply KVL to loop L1. So that is armature circuit. So we got this expression, and the voltage across this two terminal is your back EMF EB. Okay, so therefore here we are getting the expression for EA is equal to LA DIA by dt plus IARA plus EB. Okay, and the last equation express the torque equation of motor in terms of mechanical parameter. Okay, so therefore torque equation in terms of mechanical parameter Tm is equal to, where you just use the analogy between translational mechanical system and the rotational mechanical system. Okay, so therefore this moment of inertia J is analogous to mass M in case of translational mechanical system. The frictional force F0 is also analogous to F0 in uh, translational mechanical system. So therefore, what is the expression for uh, uh, torque which is acting because of this moment of inertia? So that is, it will be given by J d2 theta by dt square plus, that is the driving force required to drive this armature inertia. Okay, so that will be given by the J d2 theta by dt square plus again the frictional force. So torque required to drive this friction. So therefore, it will be given by F0 into d theta by dt. Okay, so these are your four equation. Okay, so these are the basic four equation we require, and with the help of these four equation, we can determine the relation between theta of s and EA of s. So you just take down the Laplace transform of these all those equation and rearrange the equation and determine the relation between theta of s and EA of s. So that will give you the transfer function of armature control DC servo motor. Okay. Also, we have developed the block diagram of armature control DC servo motor. And the block diagram, it is observed that the armature control DC servo motor is an example of closed loop control system. Okay. So in this closed loop control system, who is going to provide the feedback? So generally, feedback path will be provided by the back EMF EB. Okay. So that's why majorly in practice, we are using a armature control DC servo motor. Okay, because of the closed loop control system. So this is all about the basics of armature control DC servo motor. Now similarly, we have to derive the transfer function of field control DC servo motor. Okay, so what do you mean by field control? So during the field control, we are keeping the value of armature quantity to be constant, and we are varying the value of field quantity. Okay, so this is called as field control system. Okay, then develop a circuit diagram for field control DC servo motor. Okay, so during the field control DC servo motor, which quantity we are going to keep constant? That is armature quantity. Okay, so therefore, just draw the armature circuit. So this armature having resistance RA, inductance LA, and which is supplied by the constant voltage source. Therefore, the armature current IA is constant, as it is supplied with constant voltage source. So its current drawn by the circuit is constant, or you may feed this armature circuit by a constant current source. Okay, so this is the back EMF EB, which is developed across armature. Okay, so current drawn by the armature circuit is remain constant during the field control. Now draw the electrical equivalent of field circuit. Okay, so field winding has its own resistance RF and the field winding inductance LF. Okay, let's say input applied to the field winding is EF. Okay, so EF is the input applied to the field winding. Then this armature has its own moment of inertia J and frictional force F0. Let's say this is the angular displacement theta, and this is TM, motor torque TM. Okay, so give figure name to this figure for field control DC servo motor. Please draw this diagram. If you have any doubt, please ask me. Have you finished this? Yes or not? Then note down the meaning of each and every term. Okay. So what do you mean by RF? So write down the meaning of RF. That is field winding resistance. Field winding resistance. That is in ohm. Then LF is the field winding inductance. That is in Henry. Then EF is the voltage applied to the field winding. Input voltage applied to field winding. Then IF is field winding current. That is in ampere. Then define J is moment of inertia. Moment of inertia. What is the unit of moment of inertia? That is kg meter square. So in practical case, we can determine it by J is equal to m r square by 2. So what is m? M is the mass of your armature and r is the radius of your armature. So by using this value, we can determine the moment of inertia. Then last one is theta, where theta is the angular displacement. Angular displacement, that is in radian or in degree. And last one is, again F0 is remaining. F, okay. So F0 is the frictional coefficient. Frictional coefficient. Its unit is Newton meter per radian second. Newton meter per radian second. And last one is Tm. Tm is the motor torque. Motor torque. Okay, so LA, RA, these are the resistance and inductance of armature winding respectively. Okay, so here we have defined all the quantities. Then what will be your next step? Okay, so now actually start with the derivation. Okay, so we always start with the derivation with the torque equation of DC motor. Okay, so you just write down. So what are the properties? You just go through the concept of field control DC servo motor. In the field control DC servo motor, we are keeping the armature current value to be constant or armature quantity to be constant. Okay, so therefore we say that your field winding is armature winding is supplied with a constant current source. So that means current drawn by the armature is remain constant. Okay. So therefore, in general, we start with the torque equation of DC motor. Okay. So what is the torque equation of DC motor? So in general, the torque in case of DC motor Tm is directly proportional to I times Ia. So the equation number 1 for this. Okay. So write down next. So in field control machine, in field control DC servo motor, armature quantity or armature quantity is kept constant, hence constant Ia. Okay, so therefore and the field flux that is high is directly proportional to the field current IF. Okay, so we can consider this proportionality constant I is equal to AF times IF. So the equation 2 for this. So now substitute this equation 2 in equation 1. Substitute equation 2 in equation 1. So here we are getting Em is proportional to AF IF into IA. Okay. Again, this proportionality constant, we may use another constant. So Em is equal to K1 KF IA IF. Okay. So if you carefully observe this equation, so this K1 is constant, KF is constant, and IA is also constant. So we can define another constant. So Tm is equal to Kt dash times IF. So why I have used notation Kt dash? Because Kt notation we have used in the armature control DC servo motor. So here I have used another notation Kt dash. So note down what is Kt dash. So Kt dash is the motor torque constant. Motor torque constant. Okay. So give equation number 3 for this. Tm is equal to Kt dash into IF, where Kt dash is the motor torque constant. So this is our step number 1. Okay. So do you have any doubt up till now? Yes. यहाँ तक किसी को डाउट है? Am I audible? Yes or no?
Yes, sir.
Okay. So tell me the next step. नेक्स्ट इक्वेशन कहाँ से मिलेगा आपको? If you understood the derivation of armature control DC servo motor, you can easily derive this field transfer function of DC servo field control DC servo motor, because the derivation of this field control DC servo motor is simpler than the derivation of armature control DC servo motor. तो टॉर्क इक्वेशन के बाद में हमें नेक्स्ट सेकंड स्टेप क्या मिली थी, कौन सी ली थी हमने? इन आर्मेचर कंट्रोल डीसी सर्वो मोटर बैक ईएमएफ का इक्वेशन लिया था। तो यहाँ पर क्या है, आपका आर्मेचर सर्किट current drawn by armature circuit is remain constant, therefore here we don't need a expression of back EMF EB here. Okay, so therefore we may go for next step. तो नेक्स्ट एक्सप्रेशन किस पे लिखा था हमने? इन आर्मेचर कंट्रोल we have apply KVL to आर्मेचर सर्किट। ओके, तो यहाँ पर अभी KVL किसे अप्लाई करोगे? कौन से सर्किट को केवीएल अप्लाई करोगे अभी? बिकॉज व्हाट इज अवर ऑब्जेक्टिव? वी हैव टू फाइंड द ट्रांसफर फंक्शन। ओके, सो व्हाट इज द in which two parameter we have to find out the relationship? What is the input to the field control DC servo motor? First tell me. EF. Input applied to in case of field control DC servo motor is the EF. So therefore take the Laplace transform of it. It will give you EF of S. Okay. And what is the output? मोटर का आउटपुट क्या रहने वाला है ऑलवेज?
Phi of S.
हाँ,
Phi of S. अपना theta of S.
right, theta of S. Because what is the basic function of motor? Motor always convert electrical energy into mechanical energy. So therefore always angular displacement, that is theta, that is the rotation of the shaft. So therefore take the Laplace transform of it, that is theta of S. So that means here if you want to determine transfer function of field control DC servo motor, okay, so we are going to find out the relation between theta of S and EF of S. ओके, अभी ये रिलेशनशिप मिलने के लिए जितने भी इक्वेशन आप फंडामेंटल लॉ अप्लाई करके लिख सकते हो ये सर्किट के लिए, तो दैट मच इक्वेशन यू कैन राइट डाउन एंड फ्रॉम दोज इक्वेशन ट्राई टू डेवलप द रिलेशन बिटवीन थीटा ऑफ एस एंड ईएफ ऑफ एस. इज इट क्लियर टू एवरीबॉडी? ओके, सो टेल मी द नेक्स्ट स्टेप. कौन सा इक्वेशन लेंगे आप ये सर्किट के लिए? टॉर्क का इक्वेशन तो हो गया आपका इन टर्म्स ऑफ इलेक्ट्रिकल क्वांटिटी. ओके, अभी सेकंड राइट डाउन नेक्स्ट स्टेप, अप्लाई केवीएल. सिंपली आपको फंडामेंटल लॉ अप्लाई करना है. अप्लाई केवीएल टू फील्ड सर्किट. जैसे हमने आर्मेचर कंट्रोल डीसी सर्वो मोटर में केवीएल अप्लाई किया था आर्मेचर सर्किट को. सो हियर सेम वे यू कैन अप्लाई केवीएल टू दिस फील्ड सर्किट. लेट्स से करंट फ्लोइंग टू दिस फील्ड सर्किट इज IF. okay, so write down the KVL equation. Tell me the KVL equation. क्या आएगा केवीएल इक्वेशन? आप लोग लिख रहे कि नहीं लिख रहे?
Yes, sir.
Okay. Okay, so write down the KVL equation and tell me.
EF is equals to IRF plus LF DIF by dt.
Okay. Any other else?
EF equal to IF RF plus LF DIF by DT.
Right, correct. Okay, so write down the equation. Here EF, input applied voltage, is EF equal to IF into RF, IF into RF plus, what is the expression for voltage across inductor? So that is in general L di by dt. So therefore here is LF into DIF upon dt. So the equation number 4 for this. Okay. Then अभी नेक्स्ट कौन सा इक्वेशन लिख सकते हो ये सर्किट के लिए? आर्मेचर कंट्रोल में हमने बेसिकली 4 इक्वेशन लिए थे. टॉर्क इक्वेशन इन टर्म्स ऑफ इलेक्ट्रिकल पैरामीटर यहाँ पर हमने ले लिया. टॉर्क इक्वेशन इन टर्म्स ऑफ इलेक्ट्रिकल पैरामीटर. सेकंड इक्वेशन था आपका बैक ईएमएफ का. तो यहाँ पर हमें जरूरत नहीं है बैक ईएमएफ की बिकॉज योर आर्मेचर क्वांटिटी इज कांस्टेंट. ओके, सो देयरफॉर वी हैव स्किप इट. देन थर्ड इक्वेशन हमने लिया था इन आर्मेचर कंट्रोल केवीएल इक्वेशन ऑफ आर्मेचर सर्किट. यहाँ पर ले लिया केवीएल इक्वेशन ऑफ फील्ड सर्किट. And then last equation is remaining. Last equation किसका लिया था? Torque equation of motor in terms of mechanical parameter. Okay, so similarly you can write down the torque equation in terms of mechanical parameter. Okay, so mechanical torque Tm is equivalent to what? The driving torque required to drive the inertia, torque required to drive inertia as well as the friction. Okay, so therefore only two terms are there. Okay, so therefore what is the expression for torque Tm in terms of mechanical parameter? Tell me the Tm equation. J is analogous to M, mass, and F0 is analogous to F in translational mechanical system. So these are the quantities in rotational mechanical system. These are the quantities in translational mechanical system. So what is the expression for force acting because of mass M? So that will be given by M d2x by dt square. And what is the expression for force F? That is F into dx by dt, where x is the displacement. So in case of translational mechanical system, the body which can move in a straight line, whereas in rotational mechanical system, here displacement in terms of angular type. Okay, so therefore it is in radian or degree. Okay, so therefore mass is analogous to J. So therefore total torque is equal to the driving torque required to drive the inertia and to overcome the frictional force. Okay, so therefore M is analogous to J. Then X displacement is analogous to what? Theta. So therefore J d2 theta by dt square plus F0, F is analogous to F, then X is analogous to theta, so F0 d theta by dt. Okay, so the equation number 5 for this. So this is your expression of torque in terms of mechanical parameters. जैसे आप ट्रांसलेशनल मैकेनिकल सिस्टम के लिए फोर्स इक्वेशन लिखे थे, similarly we have written here the torque equation for rotational mechanical system. You just refer your table of force, torque and voltage analogy or force torque current analogy. So you will get the relationship. So same you can transform any either rotational quantity into translational quantity or translational to rotational and so on. Yes, do you have any doubt in equation 5? Yes, anybody? और कोई इक्वेशन लिख सकते क्या अभी? Whether these 3, 4, 5 equations are sufficient? Yes, we have both the equation, that is EF quantity you have as well as theta we have. So we can easily develop relation between EF of S and theta of S. Clear? So what will be the next step? So now we have applied all the basic governing laws and we have got the expressions. Clear? What will be the next step? क्या करना पड़ेगा अभी? Take the Laplace transform of equation 3, 4 and 5. Take down the Laplace transform of these three equations. What we are getting? Em is equal to Kt dash into I f of s. ये equation number 6 for this. Then take the Laplace transform of equation 4. E f of s equal to I f of s into Rf plus Lf. What is the Laplace transform of this Lf dIf by dt? While taking the Laplace transform or inverse Laplace transform, okay, always remember d by dt is always replaced by s and 1 by s will be replaced by integration of dt. Okay, so here we have d by dt. So therefore d by dt will be replaced by s and Laplace transform of if is I f of s. Okay, so this is the Laplace transform of your equation 4. So simplify this equation. Take I f of s common. Okay, this I f of s and this I f of s you can take down common. So I f of s is equal to E f of s upon Rf plus s time Lf. Give equation number 7 for this. Then take down last Laplace transform of equation 5. Here you are getting Tm of s equal to, what is the Laplace transform of this equation? Tell me the equation. क्या आएगा? What is the Laplace transform of equation 5? Nobody? Hello?
Not visible.
Not visible?
No, sir.
Okay.
And sir, someone is removing the participants from meeting.
Okay. Just a minute. So now please rejoin. Now my screen is visible to everybody. Hello?
No, sir.
No, sir.
No, sir.
No, sir.
No,
Not
sir.
visible.
Now it is visible.
No, sir.
No?
No. No, sir. No, sir.
Visible or not? Yes or no?
No, sir. Not visible. Screen
No,
is not
sir.
visible.
Not visible.
Now please check.
Yes, sir. Now visible. Sir.
Yes, sir.
Okay, sorry for the disturbance. Yes, today I have forgot to make all the student attendee. So because of that, someone has take the advantage of that access. So that's why someone has removed the student participant. Okay, I forgot to change that setting. Okay, so now no one have the access to remove or add the participant. Okay. So take down the Laplace transform of equation 5. So if you find someone doing such type of thing, so you can directly tell to me. Okay. To take down the Laplace transform of equation 5, so here we are getting s square or js square theta of s plus f0 s theta of s. Okay, so take theta of s common from this term. If you take theta of s common, so here you are getting js square plus f0 s. That is equal to E m of s. Okay, so now give equation number 8 for this. Okay. So now you see this equation 6 and equation 8, they have same left hand side. So you just equate equation 7 and equation 8, write down on equating equation 7 and 8, what we are getting? Here theta of s into js square plus f0 s equal to kt dash into I f of s. Okay, so again obtain the expression for I f of s. So I f of s equal to theta of s into js square plus f0 s upon kt dash. So give equation number 9 for this. Okay, so now almost we have got our transfer function. Okay, so what is the next manipulation we have to do? Now you carefully observe this equation 6, 7, 8, 9. So equation 7 and equation 9 have same left hand side, that is I f of s. So now you just equate equation 7 and 9. So you will get the relation between theta of s and E f of s. Okay, write down, equate equation 7 and 9. On equating equation 7 and 9, okay, so what we are getting? Theta of s into js square plus f0 s upon kt dash equal to E f of s upon RA plus S times LF. Okay, so what is the transfer function? That is theta of s upon E f of s. So this theta of s, then E f of s transfer to this side. So theta of s upon E f of s, ये kt dash जो है वो ऊपर चला जाएगा. So that will give you kt dash upon, ये डिनोमिनेटर में चला जाएगा. तो js square plus f0 s multiply by RA plus S times LF. So this is our required transfer function of field controlled DC servo motor. So in this denominator, you can also take the S term common, or if you have not taken it out it common, okay, you can take down the S term common from this term. So again, you are getting 80 dash upon S into JS square plus, sorry, JS plus F0. To take S common, so S into JS plus F0 into RF plus S times LF. So this is your required transfer function. So this will give you relation between theta of S and E F of S. Okay. So this is the required transfer function of field control DC servo motor. Okay. So we can also express this transfer function in terms of time constant. Okay. So there are several ways of representing your your transfer function into different form. Okay. One is the pole zero form, representation. Okay. Then second form is the time constant form representation. Time constant form representation. Okay. So by using any one form, you can express it either in pole zero form or either in the time constant form. Okay. So here we try to convert our transfer function into time constant form. So we just define certain time constants. So what do you mean by time constant? What is the time constant of LR circuit or RC circuit? So you just take this F0 term common from this first term. So what you are getting? You take F0 term common. So you are getting 80 dash upon S into F0. ओके सो ब्रैकेट में बचेगा, ये टर्म में F0 नहीं है, सो ये आएगा J by F0 into S plus 1. Okay. Then similarly, from this term, you can take down this RF term common. तो यहाँ पर आ जाएगा RF term common, तो ये आ जाएगा 1 plus S LF upon RF. Okay, and this is your transfer function. So now we are going to define the time constant. So first time constant, so we can define it by tau ME. So ME stands for the mechanical time constant. You can note down the meaning of it. ME is the mechanical time constant. Mechanical time constant, and it will be given by J by F0. So this term J by F0 is replaced by tau ME. Then second time constant, we can define the ratio of LF by RF. So this may call it as the field circuit time constant, because both quantities are of field circuit. Okay, so therefore you may use the notation is for tau F. Tau F is the field circuit time constant. Field circuit time constant. It is given by LF upon RF. Then third time constant आएगा आपका ये this term KT dash upon RF into F0. Okay, so उसको हम लोग एक टाइम कांस्टेंट डिफाइन करते हैं. So this may denoted by Km. Okay, and it will be given by KT dash upon RF into F0. So this is called as motor gain constant. Motor gain constant. Okay, so therefore your overall transfer function in terms of time constant form is defined like this. The transfer function EF, the ratio of theta of S upon EF of S is given by AM upon S into 1 plus tau MES into 1 plus tau Fs. So this is your transfer function in terms of time constant form. Okay. Then next step, express the time transfer function in terms of block diagram form. Okay. So draw the block diagram of given transfer function. So how is the block diagram of field control DC servo motor? So which expression we are going to use here? Because transfer function gives us the relation between input and output. So we want the relation between EF and theta of S. No, so naturally input to the system is EF of S. So try to find out the relation between EF of S and IF of S. So use equation number 7. The equation 7 gives you the relation between EF of S and IF of S. Clear? So what is the expression for IF is equal to EF of S upon RF plus S times LF. So how is the block diagram form representation of this equation 7? कैसी आएगी block diagram? EF of S multiply by what is the transfer function of this block? Tell me the transfer function of this block. क्या आएगा? Hello, am I audible?
Yes, sir.
Okay. So tell me the transfer function.
RF
How is the block?
plus
Okay.
LF.
It could be 1 upon RF plus S times LF. Because EF upon RF plus S times LF is nothing but IF of S. So here is your IF of S. So IF of S is nothing but EF of S upon RF plus S times LF. Is it correct? So EF और IF में रिलेशनशिप मिल गया. अभी क्या चाहिए आपको? हमें चाहिए अभी IF और थीटा ऑफ S. तो कौन सा इक्वेशन है? So that gives you the relation between IF and theta of S. So refer equation number 9. Equation 9 gives you relation between IF of S and theta of S. क्लियर? सो देयरफॉर क्या आएगा? नेक्स्ट ब्लॉक ट्रांसफर फंक्शन I f of s and output could be theta of s. ओके, तो क्या आएगा यहाँ पर? तो ये kt डैश इधर ट्रांसफर करो, JS स्क्वायर प्लस F0 से डिनोमिनेटर में चला जाएगा. सो ये आ जाएगा आपका kt डैश अपॉन JS स्क्वायर प्लस F0s, and this is your theta of s. So this is the, so give figure name to this block diagram of field control DC servo motor. Block diagram representation of field control DC servo motor. So what is your observations from block diagram representation of this field control DC servo motor? It is a open loop type system. Is there is a presence of feedback? Feedback present है क्या system में?
No.
No, because there is no path from output to the input, or there is no summing point. Okay, so therefore there is no presence of feedback. So therefore it is a field control DC servo motor is an example of open loop control system. आपको अगर एग्जाम में theoretical question आता है, give the comparison between open loop and closed loop control system. So at that time you can also give the example of this armature control DC servo motor and field control DC servo motor. Okay, so armature control DC servo motor is example of closed loop control system, and field control DC servo motor is the example of open loop control system. So because of this these are the advantages. Okay, so widely in the practical application we never use the field control DC servo motor. Why is it so? We are generally using the armature control DC servo motor. Why? Because of that advantage. Because armature control DC servo motor is a closed loop control system, and we know the advantages of closed loop control system over the open loop control system. Because though there is a occurrence of disturbance, okay, so our output, we always get our output in a desired one because of the presence of feedback. Okay, so that is not a case in case of open loop control system. So therefore practically in most cases we are using armature control because it is a closed loop control system. Okay, so this is all about the transfer function of this field control DC motor. Okay, so you just note down few features of this field control DC servo motor as well as the armature control DC servo motor. Features of field control DC servo motor. Write down feature number 1. तो क्या एक कौन सा फीचर मिला आपको? It is a open loop system from the block diagram. Okay, so field control system features of field control motor में आप लिख सकते हो. It is a open loop control system. Okay, and as it is open loop, therefore how is the design, control system design? It is simple one. So therefore we may define it is open loop system. Control system design is simple. Therefore control system design is simple. Then और क्या फीचर लिख सकते हो? इसके जो भी टाइम कॉन्स्टेंसेस है, दिस टाउ एम ई टाउ एफ, its value is very very large. Therefore large time constant is field control machine have large time constant. And the next feature is this type of system motor can be used only for small rated motors. Small rated motors. So these are the few features of your field control DC servo motor. Whereas, what are the features of armature control DC servo motor? पहला फीचर आ जाएगा आपका, it is a closed loop control system. Am I correct? In short, you just note down. It is a closed loop control system. Then second feature क्या है? Back EMF provides a damping, therefore, which make the motor operation more stable. So this is the second feature. Then third feature आएगा, इसके opposite, field control have large time constant, therefore armature control motor have small time constant. And last वाला आ जाएगा, if you compare based on the efficiency and overall performance, so the efficiency and overall performance of field control DC servo motor is better. As compared with armature control motor have better efficiency and overall performance. These are the few features. Again, you can define another feature, as this is used for small rated motor. The armature control motor can be rated for used for the large rated motors. Okay. Then where is the application of these motors? Servo motors. Generally, it can be used in robotics, process control system, machine tools, aircraft control system, then in electromechanical actuators. Okay, so these are the few applications of this servo motors. And that we can discuss about the torque speed characteristics. So torque speed characteristics of this DC servo motor are similar to the characteristics of AC servo motor. In the next class, we are going to discuss about AC servo motor. So over there, we are going to discuss this point, that is torque speed characteristics. Okay, so these DC servo motors have similar characteristics, just like AC servo motors. We are going to derive it in next class. So today we stop here. If you have any doubt, you can ask me. Yes, anybody? किसी को डाउट है?